So it's really so great to be part of this conference and the program. And I've just been listening to all the talks and I've been learning so much. So my name is Abigail. I'm a new postdoc in Lorazana's lab at KS NYU. Just a little bit about myself. I come from a more theoretical fluid dynamics background, using mostly theory and more traditional climate models. So this is really my first take at anything machine learning related. So I've really been learning a lot, getting a lot of good ideas, and I'm going to kind of end this talk. This is more a presentation of what I'm going to be working on and what I hope to get out of the next few weeks. And I'm going to be ending with a whole bunch of questions for people to think about. But of course, if you have additional questions, feel free to interrupt throughout and also in the end. So I'm really interested in understanding how coastal sea level is related to its drivers in the ocean interior. And just kind of following up on the previous talk, I'm not looking to, at least at this point, make predictions for sea level rise, but rather I'm more interested in understanding the physical mechanisms that result in coastal sea level. So just for some motivation, this is the Santa Monica Pier. This is a visualization of what it may look like under different climate regimes. So Santa Monica is just a little further south than Santa Barbara, so I thought maybe this would feel close to home to some of you. This is the present day of what it might look like. So you can see that the sea level is fairly low and the pier extends out into the ocean. Under a 1.5 degree warming, we can see that the sea level is starting to recede into the city. And if we were to hit a 3 degree warming, the pier is completely immersed underwater. And this is of course, related to the different emission pathways that we decide to take. So this is taken from the latest IPCC report, AR6. And depending on the emission pathways, we would hit a different level of warming, which would also correspond to how much global mean sea level we would expect to see. And we can see anything from 0.5 meter to over 1 meter of global mean sea level rise. So how do we measure this? How can we understand this? What we have over here is the global sea level average, shown from satellite measurements. So these are already a few different generations of satellites that are measuring the altimetry, which is a sea surface height. And it starts at 1993 and it goes up to present. And we can see, this is in millimeters, we can see that slowly the mean sea level is rising by several millimeters a year. And on the regional scale, however, so if we were to take the deviation from the mean, so the relative sea level, we start to see that we get lots of patterns. So this isn't a real consistent image over the entire globe. And notice that this is now in centimeters. So we have almost an entire meter between the blue and the red. So this is quite drastic over different regions around the globe. I was really surprised to see how much it varies coming into this. And you can imagine, especially along coastal communities, this can really define how we mitigate and adapt to this changing climate and the rise in sea level. So there's a lot of effort to try to understand what's happening on a coastal scale, on a local scale, and specifically around the coast. So what is this coming from? What's driving these changes? So on the global scale, when we think of sea level rise, it's primarily driven by thermal expansion of the actual water molecules, as well as ice melt coming from glaciers and sea ice that are melting and causing the global mean to rise by the expansion of volume. However, on the regional scale, it's a lot more complex. And it's determined by atmospheric forcing. So for instance, surface pressure, surface temperatures, wind stress, and additionally, bathymetry, so the distance between the seafloor and the ocean surface, as well as what the coast looks like. Is it hilly? Is it flat? That's really all going to define what the coastal sea level looks like. The water density properties are important as well. What does the salinity look like? What is the temperature? What type of water bodies are related to that region? And of course, turbulent flows such as dominated circulations, as well as mesoscale eddies, and other types of flows that may affect stratification, for instance, on a smaller scale. So this is a very complex picture. And as we know, from looking at global climate models, and especially, sorry, the courtesies coming out of this, looking at projections, for example, for the end of the century, we tend to use coarse grain models that are about 1 degree in resolution, so that's about 100 kilometers. And just to visualize this, this is the eastern coast of the United States, and this is what a visualization of what sea level might look like. And you can see that within one grid box, we can fit a few states even, which really complicates trying to adapt and understand how it's going to affect the communities. But if we wanted a very high resolution model that would simulate as many processes as possible, we really don't have the computer resources to run these in the decadal timescales that are necessary for sea level. So we've got this wide range of scales, and we're really limited by more traditional simulations. And even if we were trying to simulate some of the processes, we are still limited by the type of model, the type of parameterizations, the type of resolution. So this is an extremely complicated problem. And coming into this a couple months ago, I thought that what I would do is I would look at these different properties, and I would try to understand what's really affecting coastal sea level and how we can best understand it and weed it out more in like a theoretical perspective. But what I really learned is that this is really nearly impossible. We are very limited, and yet the clock is ticking, and we need to understand how these are related to each other. So to motivate, kind of a summary of the motivation is there is a relationship to be learned between coastal sea level and what's driving it in the ocean interior. It still is the same water. It's related by climate variability and by ocean flows. But this is a multi-scale problem. It's too wide a range to simulate on the scales that are relevant for coastal sea level. Either the resolution is too coarse or it's too high, but we cannot run it for enough time. So if traditional climate simulations can't resolve this problem, perhaps the machine learning or deep learning approach is more suited. So then the next thing really is, what data can we trust? If model simulations are limited, is there any other data that we can use, and how can we meaningfully use it? So kind of going back to my title slide, I'm interested in relating coastal sea level to its drivers in the ocean interior. And I'm now going to look at a machine learning approach to create this link. So one thing that a useful type of measurement that does not come from models can actually be found in satellite measurement, satellite data. So we've got an abundance of satellite measurements from the surface of the ocean interior that are actually reflecting the flow properties from the ocean interior. So although we can't resolve all the processes that are necessary for sea level, we know how it is related from a more theoretically guided understanding of the problem. So like we mentioned, it's related to atmospheric forcing, related to density, related to bathymetry. So all of these will be reflected in, I just chose a few properties that I could think of, as well as ones that we have measurements from satellites. But here we've got sea surface temperature, sea surface salinity, altimetry, which is sea surface height, which is similar to what I showed you earlier, and atmospheric surface pressure. And all of these properties are related, although in a complex way, but we know that they are related to sea level. And the main issue with these type of measurements is that they tend to be very poor along the coast. And this is primarily because waves interfere with the signal, as well as the land and the way that the satellite measures the actual property. So we get great measurements, pretty accurate in the interior, but not so much along the coast. On the coast, however, we have a very effective way of measuring sea level with tide gauge data. So tide gauges can be anything from a stick in the water, where you just measure what the sea level is exactly at that location, or it could be something a little more sophisticated that has radars in it. But we've got a global network of tide gauges of different sorts and over spanning a different range of times. But what this does give us, it gives us the effective measurement at that location. So it's going to contain within it already all the information that's related to the variations in sea level in the interior, as well as what's happening along that coast. Some issues with this data, just to point out, because I'll bring this back again later, is it tends to be fairly noisy, as you can imagine from real live data. So right here, we've got tide gauge data from the Battery in New York City, so Battery Park, for those who are familiar. And its range is all really from the 1850s up to present, so that's a fairly long record. You can see that there's this general trend of increasing sea level as we would expect. However, there's also a gap in data, so possibly something happened to that measurement at that location. It tends to be fairly noisy, possibly due to seasonality, storms. This is also not consistent among all locations. So just as an example, this is the Santa Barbara tide gauge, which seems a little pathetic and very, sorry, it does not cover the whole range of scales. There seems to be some sort of start-stop in noise. So there is some need to incorporate this data because it's very, very valuable, but there are some issues with it as well. So the objective of what I'm interested in doing is I'm interested in incorporating these different types of measurements that reflect both properties in the interior as well as the coast. So satellite surface measurements will reflect interior properties that are important for sea level, and the tide gauge data reflects the effective sea level at those coastal locations. And I'm interested in using machine learning to really link between the measurements, the satellite measurements, which will serve as the input, and the tide gauge data, which is the target that I'm after. So this is another way to understand what I just said. So if we take the input of these different properties from the interior, from satellite measurements, and we use a convolutional neural network, kind of more standard sense, we can learn the relationship between what's happening in the interior and eventually be able to link it with what's happening along the coast. I used a map over here, but really this is a regression problem. So this is going to be an array of the sea level at all of these different locations. So drawing from inspiration from other studies, there's this wonderful paper, Deep Learning for Multi-Year ENSO Forecasts, so kind of related to what Elizabeth was saying earlier, by Ham, Kim, and Liu. And just a little overview of what they did, because I'm drawing from that for the future. They used a convolutional neural net to connect between global sea surface temperature and heat content and 24-month Niño 3.4 forecast. So their input are surface maps, and their output is an array, which is related to a physical metric that they're looking to predict. I am not looking for predictions in the future, but I am interested in understanding this mechanism of relating surface maps to an array in that sense. They used a 3-month lag between the inputs and the 24-month prediction because they found that was a better way to predict Niño 3.4. But really the most important thing for our purposes is that they trained their network on the CMIP cluster data. So they have a whole wealth of data that's coming from the CMIP cluster, and they use that to train the network. And then they use transfer learning, similar to what Pedram introduced earlier this week, to retune the network with reanalysis data. So they're training initially on model data, and then they fine-tune the network using observational data. So drawing on this, and looking again at our problem, we really don't have that much observational data. There are only a few decades of satellite data if we're lucky. Some of these measurements are way shorter. And also looking at the target data, the tide gauge data, it's a little noisy and it's a little sparse, and that's going to be a struggle as well. So using this method of transfer learning will actually enable us to strengthen this network. So feeding on this, model data, especially pi control simulations, which means that we keep the forcing fixed, enabled us to really focus on the physical relationships between what's happening in the interior and the coast. So like I mentioned earlier, we might not trust the models to fully simulate what's happening along the coast, but we can trust them in the sense that we understand the governing equations, we understand the large scale motions, and we understand how these different physical processes interact. So in that sense, the model data is very useful. So now taking a step back, if we really try to mimic what we were looking at before between the surface data and the tide gauge locations, we can mimic this exact same process using now model data. So I'm now looking to use the same surface data only given from a model. And then predict now, so the target data is going to be modeled sea level at those tide gauge locations. So it's going to pretend to be what the observations are acting like. So we use this method in order to train the network on the model data and come up with a network that's able to relate between the interior and the coast. And we use, like I mentioned, a pi control simulation to generally describe these physical relationships. But then using transfer learning, we then retune this network using the observational measurements that are a little that are quite fewer, but assuming that our network is already pre-trained on the general physical relationships, this can create a strong link between the interior and the coast. So some very, very preliminary work that I did mostly just to discuss with everyone here and to create a basis for what I'm going to be doing. I used mostly data that we had on hand in our lab. And I wanted to come up with a network just, again, to relate what's going on in the interior and the coast and see if there's even a relationship that pops out immediately. So I used a MOM6 CM2.6 model. So that's a fairly high resolution model of the North Atlantic. It's not only the North Atlantic, but I used North Atlantic data. And I didn't have all the input data that I wanted on hand, so I used other surface data that was available. So I used surface velocities and surface temperature as input. I had to mask out the coast to make sure that I don't train and predict the same points. The target data is just hand-selected locations of coastal sea level. So I really just randomly picked 20 points along the coast, and I chose the sea level at those locations, and that was pairing the data. So I've got tide gauge locations of sea level and input of surface measurements. In this case, it's velocities and temperature. I used a very general convolutional neural net. It's important to note also in the context of causality, which was discussed earlier this week, each input and target pair is a single time step. And this is something that I'll bring up in a little bit. So just some very basic results. These are the 20 tide gauge locations along the coast. And this here is a result of the test data, one of the test cases. So the model has never seen this before. And from pre-training the network and then testing it on the test data, we can compare what the target sea level would be at those tide gauge locations compared with a prediction of what the model thinks it should be based on the surface input. And I was really surprised by how close this seems to be. So in most locations, the sea level is fairly close to what we expect it to be from the model. The difference really at most seems to be about 0.05 centimeters, which is also the kind of mean squared error that we get from this network. And if anything, this is I'm optimistic for using what I would expect more theoretically confined inputs to be for this network, and be able to utilize transfer learning also to strengthen this relationships. So this is encouraging that there is a relationship between what's happening in the ocean interior and along the coast, and hopefully we can create that link in a more physically robust way. So I'm going to summarize, and then I have some questions that I thought could use as a discussion and also assistance over the next few weeks. So to summarize, what I'm planning to do and hoping to do is looking to relate coastal sea level to its drivers in the ocean interior. I'm using machine learning to link between satellite measurements and tide gauge data, but since we don't have enough data from those sources, it's better to use a transfer learning method, which is trained on model data, and then retuned on observational data using surface input to predict coastal sea level at those tide gauge locations. And really the ultimate goal from this this type of project is not necessarily to predict what's going to happen in the future or run these like El Nino predictions of years ahead, but really to gain more insight on this multi-scale problem, because the traditional simulations are failing at capturing this wide range of scales. And by improving your physical understanding, this will really lead to better projections in other ways. So here's some smaller questions that I've been wondering about, and I'll go through them, and then I'll just leave them up and wait for everyone to comment. But one thing that I'm really curious about is network architecture. It seems that there are so many different options, and each have their own advantages and disadvantages, and this is really something that it will be interesting to see if there are any preferred methods over others. So the input format is going to be a little tricky, especially using satellite measurements, because I can choose between gridded or a lawn track. And there's a time element because the gridded data is averaged over a certain time. Model resolution is also important. How fine resolution, what type of model. So these are things that are kind of on my mind. What should the output format be? Should it be an actual array of the actual sea level, or maybe moments are a better way to understand this? That's also kind of a segue to understanding extremes that Laura spoke about. We need to match consistently between the inputs and target data, so they need to overlap in time, especially if they're gridded in some way. So that's also going to be a bit of a struggle. How to treat gaps in observational data. So just a reminder, this is what the Santa Barbara tide gauge looks like. So I don't even know how to approach this at this point. There are also geographical biases. So the northern and western hemisphere tends to have more measurements over a longer range of time. Will this affect the network in any way? I'm hoping that by trading first on model data, where there's a large coverage, that will help mitigate this issue. How to account for the lag between the interior and the coast. So it takes time for the signal to reach the coast from the interior. So possibly including more input channels, like more time steps, kind of leading up to a certain time step. More medium questions. So how will this method hold for different regions? I would expect some areas to have a very strong link between the interior and the coast, and others not so much. Does seasonality affect this at all? Are some properties more important than others? So Elizabeth spoke about this a little bit, but can I remove some data from the training? Is some data more important than others? Is anything missing? This will be also something that will be interesting to find out. The only thing I will say about predictions is one way that I can imagine using this network once it's trained is to use an input of a future climate. So for instance, what does the surface conditions look like for a future climate of warmer temperatures, and what would the resulted coastal prediction be then? And how does that measure relative to the predictions that the model is actually doing? So not running the model and having all of these components correlated, but rather taking a step back and comparing the input versus output in this way. And then kind of bigger questions that really I was inspired by everyone's talks is what else can we learn from this learning process? Is there going to be something that's unique in terms of what layers maybe we need to retrain? What are the filters detecting? Is there something that comes out of this that's bigger than this specific problem? Will I be detecting causality or correlation? So is there just a correlation between what's happening along the coast and the interior, or is there some causality, and is the interior really leading to what's happening along the coast? And finally, will this method be generalizable to other climate problems? Because all this is really doing is it's linking two types of measurements that we know are related to each other physically, but there are many different kinds of datas of this sort. So possibly this could be generalizable in that sense. So this is just a summary of all those questions in case I was going through those too fast and someone had a follow-up. And I'd be really happy to discuss any of these over the next few weeks, or if anyone wants to make any comments now or about other things, I'd be very curious to hear everyone's thoughts.
Great. So I see, oh, those are hands clapping. So any questions on Zoom? Or comments on this nice array of questions? Okay, we have a local question. We need to use the mic for the benefit of, yeah, you can go there and press the button or, oh, I don't know. Try tapping it. Okay, so press the button.
Okay, good. Thank you for the talk, Abigail. Sea level rise is in itself a fairly large scale feature, right? So you did point out that the climate model resolution is coarse, of course, relative to coastlines, but the sea level rise happens on fairly large scales and doesn't have in itself small scale structure. You get small scale structure if you compare to tide gauges because of local changes that are not just sea level rise, right? So one key point is, say, subsidence of land because there's pumping of groundwater. And that is the part that you really need to worry about when you compare with the data. How would you take that into account in your approach?
Yeah, that's a very good question. Something that I'm wondering about myself. I was hoping to be able to include bathymetry somehow, because that would help with that issue. But I actually don't have a good answer for that. But perhaps that would be something that the network would be able to learn as it's matching different time steps over a long period of time. But I can imagine that would be a really big problem if we don't have a lot of data from a certain region.
Any other comments or suggestions? I think some of these questions, sadly, like network architecture, we don't have a good theoretical basis to advise you on. But for people that may have played around with such problems, I don't know if they have any best practices. And we do have someone lined up at the mic, so I'll turn it over to Micah.
I thought is this on? Yeah. Hey. I thought I'd just follow up with a question, I guess, in terms of your questions. When you say what else can we learn from the learning process, do you have anything specific in mind when you think about that? And I mean, just following up on the architecture question for some of my work, we specifically designed the architecture in terms of what sort of math effectively we wanted the method to be able to pick up, and in terms of the work that I've done, that was, I guess, a little bit more obvious perhaps. So I was wondering if you had any sort of thoughts on, what you're hoping to learn. I guess I'm asking you about your hopes for the future.
Yeah, I'm hoping that somehow the flow properties would come out of this, and specifically in the learning process. So that's kind of what I was thinking in terms of the architecture. I can imagine different layers revealing different aspects of the flow properties and how they're related to each other. I don't know how. I think there would still be some limitation even with the whole transfer learning aspect of relating models and observations, because there are still some gaps.
Yeah, exactly.
In that sense. Yeah. So yeah, I don't have a good answer for that. This is something I'm wondering about myself.
And you may want to look at, for what we can learn from the learning process, a field called AutoML, which has sort of grand goals of applying ML even to the whole, data processing pipeline. That said, I'm not sure how much success there's been so far. I do see a raised hand on Zoom. Do you have more to say?
We could continue talking about it.
Okay, thanks so much.
Wonderful. Christian?
Yeah, I just wanted to follow up on this point also. Yeah, I think in terms of what else can we learn from a learning process? I mean, I think some of the answers were more what can we learn from a trained network actually. And there's quite a bit of work also on visualizing network layers and looking at the features. So that's also what I showed some very old results on this yesterday. And learning from what can we learn from a learning process? I think this also goes into the direction of the last talk, like which regions are we actually confident about? Where do we have still high noise? And I think for me, the interesting question is then turning this around and maybe focusing the training on these aspects where we don't perform well, or if we don't have data, then at least stop and somehow flag these points. So I think that's what is really interesting to do, a kind of a supervised learning process where you take into account where you are good and where you have high errors.
Thank you.
I had a question about is geographical bias an issue? Maybe you actually already talked it through, but could you explain it again, please?
Yeah, so I mean, looking at this, let's see if I can, oops. I just wanted the map. The map of the tide gauge data, it's not consistent over the entire globe. It's not like the modeled gridded data where I've got data at every location. Rather, there's a whole range of time evolution, of gaps, of quality, and I'm only just starting to learn about really the product of these measurements. But I can imagine how this would skew the data, the results even more, or complicate the network because it would focus more on where we have more data versus less. So this is where I'm hoping the transfer learning would help, because I would first train the model on a very data-rich environment, and then only fine-tune it for where we've got a strong relationship between the coast and the interior. But that's what I meant, is that I don't know if the fact that the geographical distribution of my tide gauges is consistent, if that would be an issue for the network. Does that make more sense?
Yeah, and I think the transfer learning approach and fine-tuning is a good one, but hopefully other people will mention other approaches. We also have another question here. Pedro?
Oh, I can't hear anything.
Oh, okay. Yeah, I think like if you can get away from with transfer learning on just one layer, then there is a lot you can do by looking at how the layers have changed in a spectrum like the stuff I showed, but also maybe just in the physical space and things like that. That can be very helpful, and it's easier than just trying to look at the whole network and try to see what has been learned.
Yeah, it was really interesting to see how yours, the shallow layers were more important. So I'd be interested to see what comes out of this.
Rose?
Sure. Thank you, Abigail. I think the presentation was wonderful. I just have a couple comments about your questions. Like, could you switch to the?
Yeah, I'll go to the summary one.
Right. So, okay. So like in terms of network architecture search, I think the general principle is that, you know, if you're not modeling the temporal data, where you're just only doing the spatial mapping, right, the leveraging like translation inductive biases in like convolutional neural nets 2D is actually, it seems to be the best of practice right now. And if you do like temporal modeling, and depending on the computational memory constraints, like if you have like equally length data, then one-dimensional temporal convolution usually the best practice. And if you have more memory, you can switch to more like attention-based methods like transformers and or even recurrent networks if your sequence is variable length. That's kind of the like folklore. and in terms of theory, I think there's very limited theory and people do architecture search, but it's not super feasible for like huge climate data. In terms of the question of gaps in observational data, we have some papers about like imputation. Basically, you need to treat like sequences as some sort of time series with missing data, and then you do like imputation and first, and then do forecasting. The other technique is you can actually model this gap as a pattern in the data, which is related to continuous time recurrent neural networks. And that's, I mean, I'm happy to share the pointers to you if that's helpful.
This is very helpful. Thank you.
Yeah, so then for the geographic bias, and so it's actually what we found is it's not necessarily the geographic bias, it's more like the data distributional shift. So you need to look at, like when you collect data from two different locations, and you need to look at whether the data actually are similar or not. So what we did was ocean current forecasting is we were basically take sub areas in the ocean and then look at whether the velocity field distributions are similar or not. And if they're different, then it creates some problem for machine learning models. So we have some new papers about meta learning, which is try to kind of find the latent structure when we move from one location to the other that can correct the bias in this type of distributional shift. For the what we can learn from the learning process, I think there's a lot of there's a lot of interpretability, explainability work, but I think for physical models, I think it's important to look at the physical metrics, whether they preserve the kind of the physics or the conservation laws we know. That's also what I talked about on Monday. And I think like the next big question is probably the causality. I think that Jakob also talked about that yesterday. Yeah, hope that's helpful. But I'd love to talk more and discuss what we can do.
Yeah, I'd be happy to. Thank you so much.
Thank you for that, Rose. And I'm not sure at the very beginning, do you also, so I would sort of favor not using recurrence, not using LSTM. There's starting to be a lot of evidence that everything can be done with some sort of either transformer, attention-based method, or feed-forward CNN. Or would you favor recurrence for anything that she's doing?
I tried playing around a little bit with LSTM a little while ago, and I did get some results, but I felt like there was I don't know, it didn't feel consistent with what I was trying, the overall picture of what I was trying to do. But I'll listen to the answer.
Yeah, so I think our experience is that depend on the dynamics of data. If it's like very non-stationary, it has a long-term memory, then sequence-based models like LSTM were split because it has this kind of memory mechanism, where like CNNs has only like short-term dependency and assumes like fixed time window. So it really depends on like the dynamics.
Okay, great.
Cool, Dorit.
Yeah, so hi, Abigail, I really enjoyed your talk. So I come from a really different angle. If you had given this presentation at a stats conference, people would say use a Bayesian hierarchical spatial model. And I think that's actually really worth it. It seems like here, people think the only way to go about this is using some form of deep learning or neural networks. And your problem, especially with your missing data, there's enormous literature in the stats community. So your problem is almost ideal for setting this up. You just need to get your hands on a collaborator who really knows how to do Bayesian spatial hierarchical models with massive data, and there's a community for that. This is just all these kind of questions you ask about network architecture. I think would actually be very interesting to see these two models compared. And the nice thing about statistical models is that you have much more control about what you actually put in, and all your questions about relationships, they are much clearly in the sense of, because you construct them, you know what's actually going on. So obviously this might actually be a really nice opportunity to learn from what you learn through deep learning approaches, and then explicitly use that in like a Bayesian hierarchical setup where you know how you use it in much more explicit ways. And especially you can really build in the spatial connection along your coastlines. And I think that's something you lose in these type of setups because it's all done so indirectly rather than explicitly.
Yeah, so let's not throw Bayesian methods out the window.
Yeah, I'm gonna follow up on that. Thank you.
There's also some sort of happy medium, at least for Gaussian processes. There are now neural processes where you don't just have to use a sort of Gaussian, you can actually have a neural network to learn part of the model that you want to use in your process model. So any other questions? I think maybe people in this room want to go get the hot pastries that are outside.
I'm so jealous.
But that was a great food for discussion. Please stay active on Slack and stay in touch with us because we would love to discuss. So thanks to everyone in this morning time. We'll do an applause.